Hello everyone, this is Johnny. Today I'd like to present our paper. It is empirical research about LLM fine-tuning training time predictions by scaling laws. As we are aware, LLM size keep increasing, and we notice and wrote the paper from OpenAI about scaling law for neural languages model. And LLM training loss were decreasing, improve with the larger n, which is model size, and a larger d, which is data set size, follow the power law. Eventually, you will see the diagram here. That's the visualizations. The right-hand side will be the formula represent the loss. And you can see the constant exponent to represent the power law-based scaling law. We think the scaling law can be the fundamental to build our prediction model. Then we do the research survey. And we realize that scaling law research most likely focus on pre-training instead of the fine-tuning. It is focused on training loss instead of the training time. There's some of the running time prediction model based on a computer architecture like a machine profile, flops, even roofline, and some of them even scan the machine learning models, understand optimizers, and using that to do the prediction. However, after we try it out without the physical model run with the data set, and the data is still large. That turns out the scaling law with the empirical time predictions can we use a small sampling to scale predictions scale up and even the scale out. So wrap up with that research question is how can the power law scaling relationship effectively predict the computation cost, which is training time in our case, for LLM fine-tuning, thereby enable efficiency in a sustainable AI infrastructure planning. Therefore, we designed two-stage methodologies. As you can see, the right-hand side diagram is pretty straightforward. Stage 1, collect the sampling. We call it SLST, scaling law smart tuning, which is hypermutant tunings follows the scaling law. Then second stage is predict the time. And they have two phases. Phase 1 is scaling law. Second phase is gradient boosting. Here I give more detail about the scaling law smart tuning. We leverage the Meta OPT model. As you can see, the right-hand side, y-axis accuracy, x-axis are all model size. Different chart represent a different data set. They're all growing up, which is complying with the scaling law. This gives us the confidence. Then making sure the loss to improve when the model size increasing and the data set size increasing. And it turns out the paper also provides suggestion learning rate and batch size. We use that to design our grid for hyperparameter tuning to make sure the loss can comply with the scaling law, and also the time will collect more reasonably. So we start only with the largest data set here. Then the example here is make sure the 66B model size loss is lower than 30B, and the data set size within the same model, and the 70K model size loss should be lower than 60K. With this solutions, we can dramatically reduce the number of the trial compared with the brute force traditional hyperparameter tuning. So stage 2, before that, I will give you a little bit insight. In general, larger N, larger D increase the time. The higher PP in LLM is actually improving the training time. When we need to run a larger model, we need more GPU. A number of the GPU G is equal to tensor parallelism time pipeline parallelism. So for that, we provide the candidate for scaling law formula. So the first one is Adams law base. So as you can see, the TA, the factors, we use the Adams law to represent the TP and also the PP. We think the Adams law can provide the better the curve to catch up aligned with the hardware. Another assumption is the power law based factors, as you can see below. And both of them are using gradient boosting to reduce the procedure at the end. The experiment setup, we use A to 16 NVIDIA H100s. Then we run OPT with the self-instruct dataset. This is the result that we have. And generally, the TA, which is Adams law factors, scaling law slightly perform better than Paul's law. That's the reason why we used Adams law as an example here to show you the constants and exponent values in here. The right-hand side, we show the example about time versus model, time versus the data set, and the G equal to the number of the GPU, and PP time TP represent the parallelism setup. For different number of the GPU, different parallelism setup, the dashed line represent the prediction and the physical line present the ground truth. And you see they are all aligned very close. This is the potential use case in our mind. So like we said before, we cannot run, or we don't have that resource to run, but we want to predict. So let's say if the model size is up to 175 billion, it's 100 times larger than 80K. And if we have a 128 GPU AI infrastructure, how long it would take? Based on our model predictions, it will be around 40 hours. So conclusion is, while using this initial sampling and the two-phase predictions, it can be calibrate the prediction model pretty well, significantly reduce the need of exhaustive and empirical evaluations. Also, this result can be strategy decisions. And in the paper, we try OPT model and also self-instruct data set, but we continually move on. Right now, we have a llama, we have a supernature, even for C, which is compute, not only for NVIDIA H100, we try AMD MI300. So all of them show same patterns. For future work, definitely scale up the model and the dataset size, and even number of the GPU from 16 to prove if we have a 128 GPU, how the prediction compare with the ground truth. And we are also working on scale outs, which is, can we use NVIDIA GPU to predict AMD GPU if we have a small sampling on AMD, and also maybe Intel Gaudi, and we also working on that as well. This is in my presentation. If you have any question or comment, feel free to reach me out. Thank you.